All right, everybody, welcome back. This is video number 2 from section 1.1 of AP Calculus. Introducing calculus, can change occur at an instant? And we're just going to go through a couple of examples here related to the concepts that we talked about with instantaneous rate of change from our first video. Okay, so let's look first at example 2 here. It says the spread of a rumor is modeled by the function r of t equals 2,500 divided by the quantity 1 plus 50 e to the negative 0.25 t, where r of t is the number of people that have heard the rumor, and t is greater than 0 is the number of days since the rumor started, for t from 0 to 30. The graph of the function r and the line tangent to r at t equals 4 are shown. Which of the following gives the best estimate for the instantaneous rate of change of r at t equals 4? And we'll slide down here a little bit so that we can see our graph and our answers. The graph gets a little blurry here. Sorry, the quality is not the greatest. But what we're doing is we're estimating the instantaneous rate of change right here at 4. And if you think about it, we talked about the rate of change representing the slope at that point, which makes it really nice because we're told here that we have the line tangent to r at the point shown. And so the instantaneous rate of change is really going to be the slope of this line that we see right here. That's the actual instantaneous rate of change of the function. So how are we going to best estimate it? Well, let's look at our choices here. Part A. r of 4. Does the value of the function at that point do a good job of representing the slope? I mean, it might coincidentally come close to it, but I highly doubt it. Really, there doesn't seem to be much of a connection at all between that value and the rest of the values that we could possibly consider. So let's look at our other answer choices. We've kind of eliminated part A, and all the answer choices in parts B, C, and D look an awful lot alike. Okay, the slope of the line joining the point 1, r of 1, and 4, r of 4. The slope of the line joining 4 r of 4 and 8 r of 8, and the slope of the line joining 3.8 r of 3.8 and 4.2 r of 4.2. So let's go through and we'll look at these lines and see. We'll do this first one here in orange. The line joining 1 r of 1 is about there, and there's 4 r of 4. So we would be talking about this slope of this orange line here as compared to the slope of the green highlighted line, which represents the instantaneous rate of change. That doesn't do a terrible job of estimating it, but I'm not certain yet that it does the best. I'm going to keep striving here for a best answer. Then let's look at the line joining 4 r of 4. There that is. And then 5, 6, 7, 8. Looks like it's over here. About 8 r of 8. And so this is the slope of the line joining those 2 points. And then the last choice here that we have, slope of the line joining r of 3.8 and r of 4.2. And you see that that one does look like it does the best job of describing the instantaneous rate of change because it comes closest to the slope of that tangent line. This leads to the first official Thomas tip of AP Calculus. When you're estimating the instantaneous rate of change at a point, it is almost always going to be the best idea to find the smallest possible interval that you can that contains the x value or t value or whatever where you're trying to estimate the instantaneous rate of change. So in this case, we were trying to estimate it at 4, and we chose the interval that was smallest that contained the point 4 r of 4 to use as our estimate. Okay, let's move on to example 2. A ball is rolling down a straight path, and its position is modeled by the function b of t, where b is feet from the starting point and t is seconds since the ball started rolling. Which of the following would find the best estimate of the velocity of the ball in feet per second at time t equals 12.5? So again, we're looking here for the instantaneous rate of change because velocity is the instantaneous rate of change of position. We haven't really talked about that yet, but we certainly will talk about that in great deal more depth later on in the course. But velocity is the instantaneous rate of change of position. And so if we're trying to find the instantaneous rate of change of this position function here at time t equals 12.5, let's use the tip that I just gave you at the end of the last example. Our goal should be to find the slope of the smallest interval that contains the time value in this case, where we're trying to estimate the instantaneous rate of change. So we're trying to find the instantaneous rate of change at time t equals 12.5. We will discard choice A because it's not a slope. It's just the value of a function divided by kind of this arbitrary value of 12. Doesn't really make a whole lot of sense. The other 3 values here are all slope values, and so they will all be estimates of the velocity of the ball. But the best estimate is going to be based on the shortest time interval that contains the value we're trying to find. So since we're trying to find it at 12.5, here we've got the interval from 12 to 13. Here we've got the interval from 9 to 16. Here we've got the interval from 0 to 25. The shortest of those intervals that contains the time 12.5, where we're trying to estimate the velocity, is answer choice B. And so that's going to be our answer that we'll choose for example 3. All right. For those of you who are taking my class, please make sure you complete the MyAP assignment that's noted at the bottom of the page here before we start our next class. And I'll see you next time as we move into section 1.2. Thanks, everybody. Have a great rest of your day.